Hello, my name is Clemens. I'm the CTO of Persival, and today I'm going to talk about the ASAM OpenMATERIAL 3D standard. And specifically, we're going to talk about how to standardize the geometry of 3D assets to be used in simulation. In the last couple of videos, I've talked a lot about other ASAM standards, like OpenDRIVE, for example, a way to define a road network for the simulation. I've talked about Open Scenario. It's a standardized way to define what dynamic elements are doing in the simulation. We've talked about the Open Simulation Interface, where you can transfer simulation data between different modules and different models in a co-simulation, for example. And you can also store this data to be processed later or accessed later, all in the ASAM OSI format. These standards have all a semantic description of the environment of a vehicle in a simulation. What they don't do is describe what the environment actually looks like, and specifically what it looks like to a perception sensor. And that's where the ASAM OpenMATERIAL 3D standard comes in. I have recorded a general introduction video for ASAM. If you don't have seen that yet, check out the link in the description. In this video and also the upcoming videos, I will go more into detail about the OpenMATERIAL standard. And today specifically, we're going to talk about the geometry of things. So let's first jump into the documentation. As always, for the ASAM OpenX standards, the specifications of the standards are freely available online, so they're all open, and you can access them via GitHub. Here I jump directly into the OpenMATERIAL 3D specification, and you see it has two general parts, the material part and the geometry part. And today we're going to talk about the geometry. You can go to the geometry chapter. And it defines a couple of things. Defines an asset file, defines also mapping of material to geometry. Those are all topics for future videos. Today we're going to talk about only the geometry itself. There's some general considerations about the geometry, for example, coordinate systems. So we have a definition of where the coordinate system are, where axes are pointing, how the rotations are done. Those are general considerations for all types of assets. And then we have specifications for individual classes of assets. And in this first version 1.0 of the OpenMATERIAL 3D standard, we've defined three different classes of objects: vehicles, human, and static environments. And now I'm just going to jump right in. And we're going to go through them one by one, starting with the vehicle. What they all have in common is a model structure. And this is the core of the OpenMATERIAL 3D geometry specification. So this standard is not another 3D model exchange standards. There are a lot of them out there that are widely used, GLTF, for example, FBX, USD, and they can all work together with the OpenMATERIAL 3D standard. So we are basically standardizing here the inside of the model and not how they are exchanged. And the core, as I said, is the geometry, the structure of the geometry. And that describes how a 3D model is actually built up. Let me actually load in Blender here an example of such a geometry. I'm just dragging and dropping in a GLTF file, and that's one of the examples that comes with OpenMATERIAL, so it's all freely available on GitHub. And you have this vehicle example here. And you see on the right side, we have this node group root. And that's what's in Blender, it's called an empty node, so it's just basically a coordinate system that has other hierarchy levels below. And you can already see the hierarchies we have here in the specification and the same that we have here. So everything starts with an empty node called group root. And that's the same for all the classes. So for vehicle, humans, environments, they all start with group root. And under this, for vehicles, we have an exterior and we have an interior. So for example, if I would hide the interior here, you can see everything in the interior disappears and you only have the outer hull. Same for the exterior, I can hide that and you see the interior. And then it goes further in the hierarchy. We have then for the exterior dynamic parts and static parts. And dynamic is not only parts that can be moved, but generally parts that can be changed in the simulation. For example, change their states. If you look at lights, they don't typically move, but they can be turned off and on. So lights are also part of the group dynamic. And you see it's another empty node here in Blender. And then we can go further down in the hierarchy. And you see here we have the doors, we have license plates, we have a whole bunch of lights, and we have the wheels. And let's actually look a little bit closer into the example of the wheels. First, let's jump back to the documentation. If I go here to the wheels, you see the wheels have, first of all, they have an index or two indices. They have an axle index and they have a wheel index. So we can identify where a wheel is based on these indices. The axles are counted from front to rear. So axle with index 0 is the front axle. Axle with index 1 is the rear axle in case of these types of vehicles. And then the wheels are counted per axle going in positive Y direction, so from the right to the left. And then we have the coordinate systems clearly defined. That's in this case center of the wheel. In neutral condition, x-axis is pointing forward, y to the left, and z is pointing up. And what that enables the users of this to do is just load this asset into their simulation engine or a simulation framework or individual simulation model as an FMU, for example. And they can manipulate it during the simulation. And you see this here. By the way, everything is referenced to one reference point that's also common for other classes. Here it's in the center of the bounding box projected to the ground. Everything is referenced to that. And then you have the individual coordinate system of the individual groups. So for the group wheel, if you look at the front left wheel, it's index 0, 1. And you see we have the origin right here in the center. And what you can do now is you can rotate it. Let me change that to Euler angles. And if I now rotate around the z-axis, z is the upwards axis. So if we rotate around that axis, we actually have the steering motion of that wheel. And we can manipulate it. And you see the wheel changes its orientation. And in the same way, you can do that in your simulation. It's as easy as that. And this name is standardized, so you know if something is called group wheel 0, 1, it's all the meshes that belong to the whole wheel assembly of the front left wheel. If I hide that, the wheel is completely gone. If you look closely here, you will see there's a brake caliper here. The brake caliper, along with the general wheel assembly, of course follows the steering motion. But what it doesn't do is follow the rotation. So if I would rotate around the y-axis is the horizontal axis here, that would generally be the rotation of the wheel when the car is driving, right? But you see here the brake caliper would move with it. That's not right. So that's why we have two subgroups here. The wheel is divided into the group wheel steering and the group wheel steering and rotating. So in wheel steering, we only have the parts that follow the steering motion, but not the rotating. So if I hide that, you will see the brake caliper disappears. That belongs to that group. And everything else is in rotating. So if I now select the steering and rotating, and then rotate that around the y-axis, you will see we rotate the wheel, but the brake caliper stays where it is. So it's this kind of level of detail that we have defined in the OpenMaterial 3D specification in order for these kinds of models to be directly loaded in the simulation and be used. So they are intended to be simulation ready. Let's go to the next class. Let's talk about humans. So for a human, it's somewhat similar. So like moving the wheel in a car, we would like to move the arm or the leg in a pedestrian. The difference is the wheel can be considered as a rigid body. The human is not. It deforms when you move your arms, when you move your legs. So that's why typically in 3D graphics, in 3D animation, you use a skeleton for this. And that's what we've defined here in OpenMaterial 3D. And this skeleton again is standardized. So the individual bones, what they're named, the whole naming convention, and also their hierarchy is fully standardized. So once you have an animation or motion model of a human, you can use that for different kinds of 3D models because the skeleton will always be the same. Let me open this also in Blender. Again, also this model is open source. It's available as an example on the OpenMaterial 3D GitHub. I'm just dragging and dropping in the GLTF here of the human example. And there you can see that's our human. And same with the vehicle, you see here, everything starts with a group root. And under that, because it's a human model, as a skeleton, we have an armature. And in that armature, we have different meshes. So we can individually have, for example, this accessory here. We have this wristband. We can enable or disable that. And we have different kinds of clothing. So these could potentially also be changed in the simulation, removing the vest or changing the vest for another one, changing the hair and that kind of stuff. And then we have the armature itself. You already see that here, individual bones. And we have the hierarchy of this. We have the root bone here and then goes up to the hip. And from there, kind of 3 ways, going up the spine and going down each individual leg. And then you can load this in your simulation and just manipulate the mesh here. And then, have this work and be animated in the simulation. Okay, third and last object class. That's the general environment. For the environment, we have defined different kinds of objects you would find in a typical environment. First of all, you have a road network, and you have other environment objects that are beside the road, like buildings or vegetation. And I can also load an example here. First clean that, and then you can drag and drop in the example. Again, also provided with OpenMaterial, just GLTF file can be dragged in here, and you can see the environment. The origin here is a little bit different. It's not necessarily the center of the bounding box projected to the ground, because the stationary environment correlates with OpenDRIVE, right? If you have a map in an OpenDRIVE format and you've defined the road network there, it should coincide with the roads defined in the 3D environment. And that's why the origin here, if you have an OpenDRIVE map, is the inertial coordinate frame of OpenDRIVE. You can also find this definition here in the specification. So that's a little bit different for the environment, but the rest is very similar. You have your group root, and then you have a hierarchy of different things. You have the terrain, for example, we can hide that. You have the road network, we can enable and disable that. And you have other environment objects. In this case, we have a couple of trees as vegetation, and you see that here. And this way you can also identify these kind of things in your simulation. For example, if you don't need the environment, you're only interested in the road for performance reasons, you can just disable all the environment objects in your simulation and just don't care about them. Or on the other hand, it enables labeling. So if you have all these kinds of objects in your simulation, you know what belongs to the vegetation. So if you want to label, for example, simulated sensor data, you can access this information in your simulation and label your points in a LiDAR point cloud, for example, that hit vegetation or the ground or a road marking. And this is all enabled here in the OpenMATERIAL 3D specification. We have kind of a placeholder for other structures. So if you have assets that don't fall into either of these three categories, you can put them in the as an other model. It says very similar structure. The basic requirement is just to have a node called group root. And then you can go on from there and define other structures. In the future, we will most likely define more classes here in future versions of the OpenMATERIAL 3D specification. Right, that's a walkthrough of the classes. In the next video, I'm actually going to show you how to utilize that in a simulation and also how to combine that with other ASAM standards like the ASAM OSI standards. We've made a big effort here in the ASAM OpenMATERIAL 3D standard to harmonize with the other standards so they work hand in hand, and that's what I'm going to show you next time. So if you have any questions, feel free to drop a comment below, and see you next time.